Okay, so what I want to do next is talk about how to use a table and how to use R in order to calculate the different probabilities that we're going to need for the normal distribution. And what I want to do first is I want to just explore a little bit about this function that I previously told you to ignore, and you can continue to ignore. I just want to point a few things out with this. So again, do not memorize what this actual function is. That part's not super relevant for us. But this is the probability density function, or sometimes called the density curve, of the normal distribution with mean mu and with standard deviation sigma. And so this is, when we graph it, it's going to give us our nice bell curve that'll be symmetric about about mu, about the mean. And yeah, so this is a probability density function. So what I want to do is I really want to focus in on this part that's underneath the square, this x minus mu over sigma. And so what I want to do is let's look at a graph of this function. Now I had to use m and s. I'm using Desmos, which is a nice free calculator, but it didn't like Greek letters. So I'm using m instead of mu and s instead of sigma, but this is the idea. And so this is our nice bell curve. And what I want to explain first is that if you let m vary, all that's going to happen is that your curve is just going to be translated horizontally a little to the left or a little to the right. So if m is 0, it'll be perfectly symmetric about the y-axis. So it'll be an even function, in other words. If m is negative, this moves over as well. And then if m is positive, it moves back to the right. And so really, m can be any value. Changing the value of the mean does not affect the shape of the graph. To change the shape, you have to change the standard deviation. And so intuitively, the larger the standard deviation, the more spread out the data is. So if the standard deviation is larger, say it's 3.2, that means it's going to have a lower peak and it's going to be more spread out. The tails over here start to have more stuff in it. If I let s go to 0, so pay attention to say the area from 0 to negative infinity. If s increases, there's more and more and more stuff there. So now there's more area underneath the curve from 0 to infinity, from 0 to negative infinity. But if s is small, it's going to be more concentrated around the mean. So again, the intuition's the same. The smaller s's, the less variation there will be. In other words, the more it's concentrated about the mean. The larger s is, the more the data is spread out. Okay, that's the idea. And I think it's worth just kind of letting these go for a second. So if s is increasing, you get the shape. And then if m is changing, that's also just going to give you a vertical shift. And let's pause this at some point. Okay, so this is the normal distribution with standard deviation 1.2. So just a little fun with the calculator here, but I think that this is important enough to talk about what the values of mu and s are going to do for us. So what I want to do now is let's think about, I want to think about going back and comparing this to what's called the standard normal distribution. Okay, so there we go. So standard normal distribution. The standard normal distribution is going to be the normal distribution where you have a mean of 0, so that everything's symmetric about the y-axis, and then a standard deviation of 1. So what you put here is actually 1 squared, but that happens to also be 1. So that's the standard normal distribution. And the reason why this is useful is that it would be really hard to figure out the area under a curve for some arbitrary curve with values mu and sigma. So if mu was 5 and sigma was 2, that would give you different areas than if you had a different mu and a different sigma. The mu part turns out not to be a big deal because that's just a translation thing and you can kind of deal with that. The sigma is what turns out to be a more important thing to take care of. So what we do in the way that we tackle this problem is we talk about what's called the standardized variable. So think about the normal distribution here, and this is the normal distribution with mean, say mu. So I'm not going to draw this, I'm not going to draw that very carefully, but say with mean mu. and with standard deviation sigma. And I want to think about how could we find the area between, say, Z1 and Z2. And it turns out what we're going to do is we're going to take this curve, and then through a series of steps, we're going to turn this into something about the normal distribution. And so the way that we do that is this is called a standardized variable. So standardized variable. And what we do is we let z be the standardized variable. So z is the value that we're going to pick in the standard normal distribution. And z is exactly this exponent, x minus mu over sigma. Okay, so that's really the only formula that we're going to need all chapter. But this is called the standardized variable. And again, what it does is it's kind of a dictionary for how to get from one normal distribution to the standard normal. Because if we can understand the standard normal, and if we have a dictionary to go back and forth between any normal distribution and the standard normal, then that's enough to know everything, right? So if we can go again from any normal distribution to the standard normal, and if we can completely understand the standard normal, then we'll be in good shape. So that's the idea. So really, this is the only equation that we're going to need to know all chapter. And the reason, again, I just want to emphasize this. If I were to have some sort of, Z was a bad choice here, so I want to fix this. But if I were to have some sort of normal distribution, so say with mean mu and with standard deviation sigma, and then I want to find this area under here. Let's color this area orange. Okay, so if I want to find that area, it's going to be hard to do. I mean, now that we have technology, we can do it actually pretty easily, and I'll show you how to use R to solve this problem. But to use a table, what you would do is you would figure out what are the corresponding values of x1 and x2 in the standard normal. So in other words, if you take this normal distribution and then shift it horizontally so that it's centered at 0, and then scale it so that it has standard deviation 1, what would be the corresponding values for x1 and x2? And it turns out that those would be, I'm going to call them z1 and z2. There's just going to be x1 minus mu over sigma, and z2 will be x2 minus mu over sigma. And so if we're looking at this area, that's going to be the same as the area between z1 and z2 and the standard normal. So here this will be centered at the origin. So we're going to have probably something like this, z1 and z2. And so it turns out that that area and this area will be the same. Now, I can't draw, which may lead you to a false conclusion that all of these are shaped similarly. They're not. If you remember, when S gets big, these get flatter and more spread out. When S is small, these get really more concentrated about the mean and much higher and larger there. But it turns out that these two areas will always be the same. Okay, so if we do this process, these two areas will be the same. Again, if you've seen calculus, this shouldn't be a big surprise because this is just a change of variables. Okay, but if you've not seen calculus, that's fine. You just have to trust me that these are going to be the same areas. So if we have this translation mechanism between any normal curve and the standard normal, it's enough to understand the standard normal, and that's where we'll go next.